All right, I think we have quorum. Let's get started. So how's everybody doing? No? What's happening? Fill me in. Well, you can't say you're doing not good and then not say anything. That's not helpful. You have another week and a half. Let's cross that bridge when we get there. Yeah, Christine.
So I can get to a place where I can go with all of the figures that make money from the collection and you know,
Okay,
and that happened within like 5 minutes.
sure.
And when I kind of turn it on itself, people I can function for a page, like it's not itself. It just keeps on itself.
It will die.
Okay, so
It will probably die. No, I would not recommend going that direction. Yeah, because every time you join, especially on a self join, that will produce like a continuously exploding amount. We can test how many rows that would produce.
So that's
Okay. Did you pre-calculate it beforehand?
like skill theories, and you can kind of like it shows you how it's I don't know, like how many flow you're involved in particular stages.
Okay.
And then so at the end, like now you do it.
Okay. That's it?
So
We can do a count. We can see. I better share because I do not want to repeat the mistake I made last time. That would be bad. Okay. So we have the page ID. Where are you? So you have a page ID to page ID table. So that's what this is. Okay. So, and you're trying to join this table on itself. What does it join on?
how you do the second.
I see. So you're trying to join source on destination. Okay. So honestly, that would be the same number of expected rows then. Yeah. So that's about 500 billion rows. Is that the number we came up with last time? I think so. What was the number we came up with last time? It wasn't that one. I do not remember. I don't know if we have it. We'd have to calculate it again, but it was something like 500 billion rows. That is for sure not going to fit. So you'll have to take a separate approach. Any other questions? What table? The redirect table. Okay. So you go to the redirect table. All right. So the redirect from column is the page ID of the column or of the page that is redirecting to another page. The redirect title is the title of the page it's redirecting to. And the redirect namespace is the namespace of the page it's redirecting to. This was somewhere. No. Hmm. Yeah. So this contains the page ID of the source page, and this is the namespace of the target. So this is the namespace of the page that we're redirecting to. So if Great Britain redirects to United Kingdom, then redirect from would be the page ID of the Great Britain page. The redirect namespace would be the namespace of the UK page, and the title would be United Kingdom or whatever the page is actually called. Does that make sense? Cool.
For the statement, it is written from the ID of the name rather than
Huh?
for the statement table. Is a statement from is the ID of the
So yeah, the page link from is the ID of the page of the source page, of the page that contains the link. Any other questions? All right. Now, we ready to talk about aggregations? All right, let's go. All right. So we left off and we were having some fun kind of learning about the aggregation interface and re-implementing them a little bit. So we re-implemented the sum aggregation, the average, and the count distinct. Is this big enough for everybody? Huh? A little bigger? Good. More? Okay. All right. So we left off with this kind of idea that the that an aggregation in Spark has four things associated with it. It has a zero value, which is the default initial value. It assumes before any aggregation. It has a reduce, which takes in a new row and adds it to the aggregation. It has a merge, which takes two aggregation states and combines them together. And we also covered last time that a merge function between aggregation states must be commutative and associative. Somebody tell me why. I'm going to ask you this question on the exam, pretty much. Yes. So, well, not necessarily in different partitions, because in order to merge, two different states, you have to put them onto the same machine, and they have to be within the same partition. But when we do a shuffle after after the initial aggregation, we do a shuffle and we send all the aggregation states around. And you have a machine or a thread that's receiving these aggregation states through the network. There's no guarantee what order they're going to receive them in over the network when stuff is being sent and received. So this has to be very order agnostic. It can't matter what order these are merged in. You have to wind up with the same end state. Does that part make sense? Yeah. Yeah, this is a core component of what makes Spark a distributed system, is this merging idea. Because there are other data types in distributed systems that I talked about in my distributed systems class, namely CRDTs, which are insanely cool. We're not going to cover them here, but they have a very similar idea in the sense that if you have two states that are evolving on different machines and you need to reconcile them and combine them together, you can merge the two states, but the merge needs to be commutative and associative. And these data structures in distributed systems have additional constraints in the sense that the merge has to be, monotonic and such and such. We're not going to talk about that. But the fact that things need to be commutative and associative is a core part of the distributed nature of this. Questions on the structure and what all these methods mean? Do we remember? Is it kind of loading in from cold storage over the weekend? Good. All right. So when we left off, we were talking about, global aggregations. So these are aggregations that are not over a particular key, and those are really easy to think about, right? So we'll pass in an aggregation state class, and this is the kind of generics voodoo that we were discussing last week in the sense that we can just pass in a class, and since all of the classes that we're going to pass in here have the same interface, we can just use Python's duck typing naturally to do that, which I think is pretty cool. Statically typed languages have generics to make up for not being dynamically typed. But yeah, that's fun. So this is not a piece of code that you would have to write. This is more of a conceptual illustration of what Spark is doing for you. So we can kind of just see it in a little itty bitty piece of code. So what it's doing for you is, for every partition, it's going to create this is for a global aggregation, not by key. For every partition, it's going to create a single aggregation state, and it's going to loop through all the rows in that partition. It's going to add them all to the aggregation state. And then once it has, one aggregation state per partition, it'll send all the states to the same place and merge them all together so that we have one value at the end. That makes sense to everybody? Okay. Now, how does aggregation by key differ from that? Aggregation by key is you have one final aggregation state for every key that you aggregated on. So, if we have a table of shirts and we have one column for color and another column for price, and we wanted to see, okay, what's the average price of a green shirt, or what's the average price of a shirt per color? We would group by the color and we would take the average of the price. So we would have an aggregation state for the average for every color. Good? Good. Okay. So how we initially did this is when we did the hash aggregation, we had, this dictionary of aggregation states that would map from the key to the aggregation state. And we would loop through all the partitions, and through each partition, we would find the aggregation state that pertained to that key, and we would increment it with the reduce function. I said last time this was cheating. Why is this cheating? Right. We're keeping this global dictionary across all the partitions in our system. So every partition has access to the same dictionary of aggregation states, which is not how it works in a real distributed system, right? Because that means for every single row, if you kept this dictionary somewhere, for every single row in the partition, you would have, a bunch of machines that are all computing separately, but every time they wanted to update the aggregation state, they would have to call in to whatever node has this global aggregation state dictionary. So that would completely destroy all the parallelism that you have and defeat the purpose of using a distributed system. So we can't do it this way. So how are we going to do it? How are we going to aggregate this by key? Yes. So this is a little different from how Spark does it. But in essence, that's what it's doing. So what we're going to do right now is for every partition, we're going to create an aggregation state dictionary. So instead of having the aggregation dictionary up here, we're going to have it down here. And we're going to create one for every partition. So when we create one for every partition, we're going to have, an end state per partition. But that also means we're going to have a bunch of partial results, and all of these partial results are going to happen per partition. So let's look at what happens when we do that. So we're going to loop through every partition, and we're going to print out the result per partition. Okay, so we're printing out the result per partition, and this is what we get. So the first partition came up with these aggregations, the second partition came up with these aggregations, and the third partition came up with these aggregations. So all these aggregations live separately, and they are different aggregation states. So we have one aggregation state per partition per key. So we see that this true key and the false key are replicated on every partition. We want to not do that. So we need to combine all of the aggregation states that are related to true into one, and then we need to combine all the aggregation states that are related to false in another one. So how do we do that? We got to shuffle. So we got to take, all the aggregation states for a particular key and send them to the same machine. That's called a shuffle. And so how we're going to do that is, let's see. So right now, what I'm going to do is, so we're going to have one aggregation state or one aggregation dictionary per partition. So after we're done aggregating everything, we're going to shuffle it. Or actually, what we can do is shuffle partitions. And what this is going to be is it's probably just going to be a list of empty lists for now. And we're just going to make it the same length as our original partition list. And so then what we're going to do is we're going to take every element, every aggregation state for this partition, and we're going to send it to the correct shuffle partition. And everything with the same key is going to wind up in the same shuffle partition. Got it? Okay. What do you mean?
This is the same problem if we tell them to the same place, but ideally you can have one thing also one place and another place stays there.
That's what happens.
Okay, but you're putting it all in one.
No, we're not going to put it all in one partition. So this is going to simulate the machine going through its list of aggregation states and sending them to a different one, depending on which key it is. So what this is going to do, yes, so for aggregation state, or it would be key, for every pair of a key and an aggregation state in our aggregation dictionary for that partition, we're going to send it to the correct other partition. So right now we're pretending we have 3 processors around somewhere, and each processor is only using one partition. That's a little bit simplified because Spark in real life can have many partitions per processor, but this is only to illustrate the idea. So right now, when we're doing our shuffle, we have, so we need to take the key and we need to hash the key, and we're going to mod the hash by the number of shuffle partitions we have, and that's how we know which partition to put it in. Does that make sense? So here's how that would look. And then key. We're going to hash the key, and then we're going to mod it by the length of the number of partitions we're shuffling into. And so that should give us which partition we're sending it in. And so then we're just going to add it to that list because the shuffle partition is just a list in this simplified example. Okay. So let's actually okay. So we have our shuffle partitions for everything. So now I'm going to show you what these shuffle partitions look like, and this will make sense when we see it. For shuffle partition in partitions. And honestly, let's try that and see what happens. That was wrong. Oh, wait. This needs to be dot items. Okay, now what happens? List object has new attribute items, of course. Well, actually, we need to append both the key and the aggregation state. And this one would be items. That's wrong. What did we do wrong? So the goal here is for true to be in one of the partitions, for false to be in the other partition, and for another partition to be empty because we have 3 partitions, but we only have 2 keys. But it looks like it's duplicated for everything. So what am I doing? Oh, I see what the problem is. This is an encapsulation issue. Okay. Does anyone see why that was the problem? So that multiplication syntax that Python uses, when we take the initial list and we multiply it by a number, you're basically taking that list and replicating every value of that list by the amount that you multiplied it. The problem is that when you have a list, that list is actually just a pointer to an object. And so it copies the reference to the object, but it doesn't copy the object. So we can see that I'm going to make this multiplied by 2. So then we know what foo is, which is just that. Well, let's say we wanted to add something to the first list and not to the second. what would probably happen, let's see if that does happen, is that one is added to both lists and not just one, because it actually refers to the same list. So that's what was going on. All right, so let's try that again and see what we got here. All right, that is exactly what we want to happen. Okay, so this is before the shuffle. So we have a true state or a true key and a false key and an aggregation state for both of those keys on every partition. And after the shuffle, we have all of these aggregation states for the same key in the same partition. So this is exactly what we want. And this is what happens during a shuffle. Make sense? Okay, so now we need to go through each shuffle partition and combine the aggregation states for every key. So what do we do? Yeah. But we have to be careful. We have to be careful about doing the merge because we can't just merge everything. We have to merge them within keys.
Right, but if you do it per partition, then it's already done it.
Well, not just per partition. Even within the partitions, we still have to do them per key because you could have multiple keys that are sent to the same partition.
How that little mistake, we separated and just stamped one of each partition.
So So we don't have one partition per key. We have we have one partition per key, but we don't have one key per partition. So let's say we were aggregating on something besides a Boolean. Let's say we were aggregating on numbers instead or strings, and the key was a color. And so you might have all the things for green and all the things for purple sent to the same partition just because the hashes match. Yes, but you won't have any greens or purples on other partitions. So you can still have multiple keys per partition, but you won't have the same key on multiple partitions. You know that? You have to loop through the partitions and we have to loop through the keys. So if we remember the default dictionary from last time, what we're going to do now is we're going to loop through the shuffle partitions. And we're going to aggregate them by key. So we're going to keep these aggregations in another default dictionary. And we're still going to initialize it with the default value because we can do that. And then what we're going to do, we're going to say for key and aggregation state in the shuffle partition. We are going to take the aggregation for that key and we will do a merge with the key that's already there, if it exists. And the default value is just the empty value. And so if you merge the empty value of an aggregation state, like the default value, if you merge the default value of an aggregation state with any other aggregation state, you should wind up with the same value. That's called an identity. Yeah, it's the zero value. It's kind of like how 1 is the identity for multiplication and 0 is the identity for addition. You know, you take this value and you perform this operation on the identity value and any other value, you still get the other value. So that's what it should be. And we need to merge them together, not urge them together, merge them together. We can urge all we want, but we still have to write the code. We'll take the current value for the key, and it doesn't matter if the key is not there, it'll just be the default. And we merge the current aggregation state in there. And once we're done going through all the aggregation states, we should create, kind of another Actually, yeah. So we're going to create another one, post aggregation partitions. It's just going to be there. And so then we add everything aggregated. That's not how you spell post. And then it's just this thing. Okay. And so then we should have for post aggregation in post aggregation partitions. It would just be yay. See what we get here. Oh, something broke. What's broken? Default dict is not defined. That's because there isn't supposed to. Hello? Where is it? It's because there isn't supposed to be an underscore. Aggregation is not defined. Oh, it's plural. More problems. Wait. Did I just spell it wrong at some point? Oh, I did. More problems. Integer object has no attribute finish. Oh, I already did the finish. That's why. Which means we actually just print it out. Well, all right. This is exactly what we want. So we've gone through all the phases. We started with the initial aggregation values, between all the partitions. So they're all mixed. And then we shuffled them to the other partitions. I should actually print out kind of a delimiter. Shuffling. And then aggregating. Okay. Okay. So this is what we wind up with when we do all the aggregations within the partitions. And then we shuffle them. And then after we shuffle them, this is what we wind up with all the aggregation states within the same partitions for all those keys. And then we need to merge the aggregation states for the same key within the partitions together. And this is what we wind up with. This is how Spark executes your aggregations. Questions? During an aggregation?
Can I partition my data into UIs that I'm having the aggregation?
I mean, you can, but that's still a shuffle. Yeah, you're just pre-shuffling. It also depends on how smart Spark is. I do not have a lot of faith in Spark's intelligence. So does everybody understand hash aggregations? That's one strategy. Another strategy is sort aggregations, which we didn't even start talking about last time, and I meant to cover both last time, but it's better to cover this concept slowly and thoroughly because it's really important. So is everybody ready to kind of shift gears? We're going to talk about sort aggregations. Good. Okay. So the sort aggregation stuff has a lot in common with the hash aggregation stuff, but the mechanism for it is just a little bit different. That is all. All right. So for the hash aggregations, you'll notice that when we're initially doing the aggregations, for every key that we're aggregating on, we keep an entry in a hash table. The problem is if you have, a memory constrained application, then using a hash table might not be the best option for you because, having this kind of in-memory data structure uses a ton of memory, but not only that, you have to keep all the aggregation states at the same time in memory while you're doing the entire aggregation. So one way to avoid that is to use a sort aggregation. And the sort aggregations, what they'll do first is they'll take the aggregation key, they will sort your partitions by the aggregation key, and then they do the aggregation. And so what this does is when it's sorted, you know that all of the rows having the same value for the aggregation key are all stored contiguously together. So if you start processing one aggregation key and you keep going down this list, and then you see a different key, you know that you're not going to see that same key again. So you can just emit your aggregation state from there. And you don't have to keep an intermediate hash table in memory while you're doing this. So a sort aggregation can be much more memory efficient than a hash aggregation. Make sense? Okay. So we're going to go over how that works. All right. And I'll put the sample code on GitHub when we're done with it. I didn't want to put the earlier version of this that we had last time because we were cheating and I don't want to put that on there. Because we weren't done yet. Okay. So let's do some sort aggregation. All right. So now what we need to do is we need to take each partition. We need to do a p dot sort. And our key is going to be the aggregation key. And if you recall, the aggregation key is a function, is an anonymous function or potentially any other function that takes in the entire row as an argument and then outputs the aggregation key. So that's what these two things are. Everyone remember that? And this is just so we could generalize it. Okay. So does that part make sense? So the sort function, I believe, also takes a key for this. Let's look. And then you should be able to define the criteria somehow. Yeah, there we go. Okay. So you can submit a function with the sort method that defines the key for your sorting. So the key for your sorting is you're not going to sort by the elements you're sorting. You're going to sort by the results of this function that I'm sending. And you're going to pass in every element to this function to get your sorting key. Make sense? Great. Hello? Are you gonna... Did you die? No, the machine is still alive. Help. Uh-oh. This is not good. Okay, so it's just Chrome. Oh, there we go. Okay. Slight hiccup. We're going to pretend that didn't happen. All right. So we're not going to be dealing with a default dictionary anymore because we don't need to keep all the aggregation states in memory at the same time. So what are we going to do instead? We're going to keep a current state for the aggregation key. And it would just be an instance of this class. And it would be a current key equals the first element of the partition. All right. So we have to be careful not to accidentally exclude rows here. So what we need to do first is we need to loop through everything, and whenever we see a key that we don't have anymore, we can add it to the next shuffle partition. So we're going to see the initial key, and then we're going to loop through everything. And then the second we see a key that is not the initial key, we're going to update the current key and then keep going until that's over, and then continue generating these aggregation states. All right. Yes, with key row is not equal to the current key. Then we will update. Well, we're going to update. Yeah, we're going to update the current key to be the aggregation key of the current row. What we also need to do is we need to add it to the shuffle partitions. Or no. Yes, we do. We need to add it to the shuffle partitions. So current key, hash, and that's the length. And then we would need to add the, let's actually split this up. Or not. And then we're going to have the current key, and we're going to send the current state. And then for that partition, we're done. And so then we just need to do that for every partition. So after that, we should be fine. And then we would need to do basically the exact same thing for the shuffle partitions. So let's kind of see what we've got going on here so far. I did not spell for correctly. All right, let's see what we got. Error. Lovely. Wait, sort takes no positional arguments. Oh, I have to specifically label this as the key. Whoa. Some aggregation object. Oh, I see what happened. So we need to still print the fish. Okay. So it seems like we're not actually updating anything right now, which means what are we doing wrong here? This is a lot harder to get right on the first try than the hash because there's just more going on in terms of the code. Let's see. We need to actually reduce it. We need to add. We also need to create a new state. Reduce current key. Okay. And then let's see the Hmm? So we're not merging them yet. So we're taking this one step at a time. So right now we're going through all the partitions, and after sorting the partitions, we're going to create the aggregation states per partition per key. So that's what I'm trying to do here, except this is much more difficult to do on the fly than the hash aggregations are. There's just a lot more programming. It's a lot less conceptual and a lot more of just the nitty-gritty aspects of it. So it would just be the current key of 0. Aggregation key. Okay. Okay. What is going on? No, it's the aggregation column. We need to add the aggregation column of the first row. That's better. And is that the same as the first one? It is not. Probably because we haven't. Why is this different every time? Okay. Okay. I don't know what's going on. I'm gonna have to look at this more closely after class. Okay. I actually have written this before at count. I have written a custom sort aggregation before. The reason I had to do that is because by default, Spark will kind of sort your partitions first and then do the aggregations to create all the aggregation states. And then once it creates all the aggregation states, it will shuffle them out to everything else, just like in the hash aggregation, and then sort those aggregation states by the aggregation key and then merge them again. The problem was in my particular implementation, I had an aggregation state that was too large. The aggregation state was way too big to have all of them exist in the cluster at the same time. And so what I did to kind of get around this problem is Spark has a method called it has a method called sort within partitions, and it has another method called map partitions. And so the combination of those two things will actually allow you to implement a sort aggregation without without pre-aggregating first before the shuffle. So let's see. Iceberg API. Yes. Hmm? Yes. I pre-shuffled specifically to avoid the pre-aggregation because I didn't want Spark to be doing that. And unfortunately, when you configure Spark and you tell it to do an aggregation, there's no mechanism to not tell it to pre-aggregate, which is annoying. And it's only really relevant when your aggregation state is much larger than the result is. And that doesn't happen a lot. It does happen with aggregation functions like count distinct. So with count distinct, when you count the number of distinct values for a column, whether it's within a particular key or not, um, you need to keep like a running tally or a set of all the things that you've seen before. And we did that, in our implementation of the aggregation states. Up here. And the problem with that is, if I was holding a count distinct aggregation state for every key on the cluster at the same time, I would run out of memory. And so what I needed to do instead was I would use where's RDD? Actually, no. Data frame has this method. Data frame has this method called so you can repartition the data frame. Is the repartition. Okay. So you can repartition a data frame by a specific column. So you can do kind of a pre-shuffle before you do anything else. So you can set the number of partitions and you can set the columns that you're partitioning by when you do this repartition for a data frame. So I would repartition by my aggregation key, and then I would call this other method after repartition called, where is it? Sort within partitions. So you can repartition it by the aggregation key and then sort the partitions after you do the repartition by the aggregation key. Then you have everything you need to do a sort aggregation. How you do the sort aggregation is another method called map partitions. Really? Where did it go? Why are you like this? All right. And so after you call, the repartition by the aggregation key, and then after you call sort within partitions, you can then call the map partitions function or the map partitions method, which actually takes in an entire partition for you to process at once. And how it does that, it streams it through an iterator. So you'll notice that this custom function that's being defined in this example isn't a function in Python's traditional sense. It's a generator, which yields an iterator. So what this generator does is it will kind of loop through the rows of the partition as they come into memory. So what Spark will do is it will, maybe store the rest of the partition on disk, deserialize a small part of them, and put them into memory for map partitions to consume it. So it's streamed, which is what makes it so efficient. And so this is how we did it, right? So when I kind of rewrote these aggregations with a custom sort aggregation, I use this technique with repartitions and sorting within the partitions first, and then using map partition to basically do what I'm trying to do right here.
In order for it to be partitioned, do you have to sort the video?
You don't have to sort the data to repartition. You just need to guarantee that everything in the key that you're partitioning by goes onto the same machine. You don't have to sort it to do that.
How does it do that?
So it's like, let's say you have your cluster. And in this example, we're going to have 4 nodes. So we're aggregating the price of shirts by color. So this one, so we have green, and then we have, red being stored over here, and we have green being stored over here, and then we have red being stored over here. And let's say this guy also has green, and this guy also has green. So these are the current rows as we see them pre-partition. Post-partition, what's going to happen is everything with green is going to be sent to the same machine, and everything with red is going to be sent to the same machine. So all the greens go over here, and the green just kind of stays there, and all the reds, let's say, go here. So you don't need to do any sorting for this to happen. It can do this row by row.
But at first, before we do it row by row, I should go through the data and then find these keys. And decide which partition is given each key for index 7.
Well, yeah, but it doesn't have to find the distinct key. It doesn't have to look through its entire, data set. It can do it lazily as a stream.
So if you look through the first one, so okay, this is my first one, I'm in the subject here. But it has to know when that one finds like this one finds a red first, you decide to send this here. If this one finds a green first, it has to know if any of the other nodes are designated a place for the greens.
Well, yeah, but that's something the coordinator would take care, right? So the protocol, this also gets to the idea of distributed systems. Teaching this in depth is hard without distributed systems knowledge, but like what happens is we have a protocol that all of these nodes are following. That this is just an example. This might not be how Spark actually does it, but we have the hash function example, and that's how we calculated which partition every key was going to go into. Hash functions are deterministic. So regardless of when it's executed and where it's executed, you're going to get the same answer. And so what happens, let's say the hash value for green is 46. And so every node is going to know that the hash value for green is 46. So this knows that the hash value for green is 46. This knows that the hash value for green is 46, and so on. The nodes also know how to map from a hash value to a partition ID. And that would also be part of the protocol. So in our incredibly simple example, what we did is our cluster has a fixed number of partitions that it's going to send to, and every partition has been assigned to a specific node. So our mapping just looks like, this hash value modded by the number of nodes or the number of partitions that we're shuffling into. Let's say it's 4. And so then this value would result in a 0, a 1, a 2, or a 3. Those are the possible values for this expression. And so based on which one it is, we would send it to one of these 4 machines. So if it's a 0, then it goes here. If it's a 1, then it goes here. If it's a 2, then it goes here. If it's a 3, then it goes here.
Okay, then in our example that you know above, didn't we sort before we created the aggregation states?
In this sort aggregations?
Uh-huh.
Yes. So that is part of the aggregation. It's not part of the shuffle. So the aggregation and the shuffle are 2 separate things.
So we need to do a sort aggregation. Is it shuffle first or sort?
It will sort first, do the aggregation, and then shuffle, and then sort again, and do the aggregation again.
Like source, aggregate, shuffling sorts.
Aggregates.
And then you mean that second aggregate, you mean with the. You mean the merge.
Yes,
And the first aggregate, you mean the.
yes. Does this spaghetti make sense? Okay. All right. Now, I was planning on going through this more in depth in class. If you want to watch me struggle, then we can for the next 12 minutes so I can get this right. I will get it right, but it might take a while. Or we can just go into office hours. Yeah.
So let's say we move over the unit to one machine. You see like the machine not in that memory, but it means we would have a.
We're not in the,
Something like when we move over the step to one machine,
yeah,
that machine can hold all the values, so we have it at.
that has happened before. So a special example of this kind of shuffling gone wrong is we had a data scientist who he would use the string null instead of the actual null value. And so Spark thinks the string null is like a valid string and it's a valid aggregation key. And so it's going to send the string null to one machine, and all of the values for this null string are being streamed to one machine. Now, this table had 100 million rows in it, and 90% of the values of the columns that we were aggregating on were null. So 9 out of 10 rows in this example were being sent to a single machine, and that crashed it. So that does happen.
Okay, so if you have lots and lots of different keys, we consider doing so I actually consider lots of keys.
So that is another real key difference here in that if you're going to do this, custom sort aggregation technique versus using the hash aggregation, that's one thing to consider is how many keys are you aggregating by, or how many unique values does the aggregation key take? So in this example, for true and for false, we only have two unique values. And that doesn't change for Booleans, whether we have, a billion rows or if we have 100. And so storing aggregation states for the most part, storing aggregation states would be really easy because we only have two of them maximum on every machine. And so we can, shuffle those around easily. We can store them really easily, and that's fine. So you can use a hash aggregation when you have a small number of unique values for the aggregation key. The hard part is, like in the example I mentioned earlier, we had a lot of different unique values for the keys, and the aggregation states themselves were huge. And so we couldn't even afford to do it the way Spark does it. We had to do it ourselves. I had to command Spark, okay, repartition it on this column and now sort the partitions by this column. And now I'm going to aggregate it myself because I can't tell you how to do it right.
So that's a small number, I mean, obviously. So when you're talking about like times and choose, that's and adding the big value, calculation serve, and how many values is enough that you will need in the civil?
I mean,
So
I mean, I don't have a hard and fast number for you. It also depends on the size of the aggregation states. But you can probably store, at least a few million aggregation states before having to do the special sort and repartition manually.
Okay, so what about not doing as in each or are you saying that the only way to be the silk one is to get many?
Well, that's only if you have a large number of unique keys and you have huge aggregation states. You'd only need those two conditions to be true in order to do something like what we did with map partitions.
So TriSpark does have a sort aggregation.
Yes, PySpark has a sort aggregation, and there is actually a config somewhere in Spark that will tell it to use sort aggregations instead of hash. Yes.
Actually have to change it in the Spark to do it.
Yeah, you have to like change it in the Spark session. It's really stupid. I don't know why you can't select it like per aggregation manually, which would be ideal. I don't know why you can't do that, but you can't. Okay. Not ort, sort. It's bypass merge. It's gotta be in there somewhere. Sort fallback threshold. Yeah. Where is it? It's interesting. It's somewhere in here, in this giant monstrosity. Okay. It's somewhere in here. I'll find it and show you on Thursday. But you can activate that as a setting.
Try it. If you have like a half rate of then you're like, oh, this is something.
Yeah. The difficulty though is that map partitions is part of the RDD API, and honestly, this is the only thing that data frames doesn't have that RDD has that I really want. I'm really annoyed that you can't use map partitions on data frames because I'm having you in this class use Spark Connect. And Spark Connect doesn't actually have the RDD API available to you. And so you can use map partitions if you submit the job to EMR, like how you're supposed to do it when you submit it for the project, because you're not using Spark Connect over there. And if you want to use Livy, you can also use map partitions when you use Livy. But I wanted to simplify your setup. And so I am having you use Spark Connect instead of Livy. And so that means we're not really going to be able to do something like this unless we use Livy. And so I will not be assigning anything that requires you to use repartition and then map partitions. Because nothing in default Spark has aggregation states that large. Go ahead.
Um, when I had a data frame and let's say I create a new column, I get a column, and name something and a concept function to it.
Mm-hmm.
Is it going to operate on every row that I data frame? That's what that means. Like a new column means.
Yes.
How would you? How would you know that?
With column adds a column to every row. It's a row-wise operation.
Oh. So this one is what is the row-wise operation. The MC passing the function between rows is makes makes that function divide up.
Yes. And the arguments that you pass to a function when you're using with column come from the row that it's a part of. You can't mix rows using with column.
So if I pass column it will refer to the value in that column in that
row. In each row. Yes.
And if it's European row guys, do I have to pass the row into it?
Not the entire row, you pass it by column.
I do have to have argument.
No, it's not like the RDD API where you deal with rows as an entire unit. Everything in the data frame is separated into columns. Now you can combine all of your columns into a single struct column and then pass that in if you wanted to.
If I'm doing that well, if I'm passing a function in, is that considered a program?
Functional for, I mean, I wouldn't say so because what you're really doing is you're kind of just defining a UDF. It depends on how you want to think about it. The RDD API is much more functioning than the data frames API. The data frames API is heavily based on SQL, or as I like to call it, Squirrel. But it should be called Squirrel. I don't know why it's not called Squirrel, but I'm disappointed it isn't.
So, different of data frames, what I'm writing is based on SQL, but I'm not taking them these units.
No, you're fine.
Because I think what I got when we were talking about the function programming and you getting away from aggregations and doing these things so it can be done in separate places.
In what?
In separate places.
So, like, there are ways you can do that if you have knowledge of functional programming because Spark has those options available to you. So, like, when you do row-wise operations in Spark, this is over like arrays. You can have, functional programming constructs with arrays. And this is where, Spark SQL actually does have heavy functional programming is when you're dealing with arrays in memory. So in the early examples in this class, right, we had, I don't even know where these are anymore. We can go and look. They're somewhere. Actually, I put them into the examples. So we can look at them. This is taking its sweet time. But yes, in general, Spark Squirrel is better.
So if really something is being done row-wise, it means it can be distributed.
Yes. Well, everything in the SQL API for data frames is distributed, pretty much. Using SQL doesn't make it any less distributed.
Well, if I'm doing joins or doing something on my whole data set, it can be distributed.
It has to be because you would have to be shuffling.
Well, I guess maybe that was what I was trying to. I
Yeah,
mean, my data is so it's by default distributed.
yeah.
Doing stuff that requires you to shuffle on the data, but you're not really using the power that the distributed system.
Well, you still are, but there's inefficiencies when you shuffle because there's network overhead. That's why, training like a decision tree in a distributed system is super slow because it has to do all of this sorting, and the sorting requires a shuffle. Where did it go? Oh yeah, this is the example where we looked at every word that starts with A. So every word that starts with A in the same line, you can split the line into an array and then loop through every member of the array in the same row. That's the functional programming. This is a very functional style. That's the part I was talking. So for RDDs take that to another level, and they themselves are like made with functional programming constructs. So you have RDD.map and RDD.filter and such, right? And that follows the same pattern that this does over here. Data frames are more heavily based off of SQL. Anything else? We're done. It's office hours now. If anybody has questions. All right. And I will get this under control by Thursday so that we can actually see how it works.